Here again, we look at our familiar problem of solving this matrix equation, AX equals C. Again, this is solving a system of, in general, M equations with N unknowns. And we'll be looking at two methods. The first is using the inverse matrix, and the second is using Cramer's rule. After watching this and the next video, you'll be able to first recognize whether the square matrix A has an inverse, which we'll denote as A raised to the minus 1. And if it does have an inverse, you'll be able to find it and then solve for x and solve this equation. You'll also be able to use another kind of rather simple technique using Cramer's rule to solve for x. So in this first video, we'll talk about the inverse matrix. And this is covered in section 10.6.1 of Greenberg's book. So for scalar algebra, we can solve the system AX is equal to C by division. So we have a problem of A multiplied by X is equal to C, and we can solve for X by simply dividing C by X. But for matrix algebra, division is not defined. But we can solve the system and again AX equals C is our system by multiplying with the inverse matrix. And the inverse matrix, which we'll denote as A raised to the minus 1 power. So this is the inverse matrix. And it's defined such that A minus 1 times A gives the identity matrix. And just to remind you, the identity matrix has elements equal to the Kronecker delta, where the Kronecker delta is equal to 1 if I is equal to j, and equals 0 if I is not equal to j. And written in matrix form, this would means that the only non-zero terms are ones on the diagonals. Okay, that's just to remind you about the identity matrix, and we're going to look at a matrix. We're going to actually build the identity matrix when we derive how to solve for the inverse matrix. So keep that in mind. And if we have the inverse matrix for a square matrix in which the number of equations is equal to the number of unknowns, then we can solve this system AX equals C by pre-multiplying both sides of the equation by the inverse. And you'll notice that A times its inverse gives I on the left-hand side times x. And I times any matrix is just, by definition, that returns the matrix itself. So this is how we can solve for x using the inverse matrix once we're able to solve for what the inverse matrix is. So the topic here is how to solve for the inverse matrix if A is square. So what I'm going to cover is how to solve for the inverse matrix for a square matrix. Now consider the determinant of A. And I'm going to write down again the definition of it, the formula for the determinant. And in this case, we're going to sum over J. We looked at a determinant where we could sum over one indice or the other, but this time we're going to sum over J. And so the first part is the element Ji of the matrix times the cofactor of element Ji. And here I is fixed. So again, this is a sum over n numbers with I fixed times, which is the product of element Ji and cofactor Ji. So let me write that down. So A Ji is the Ji, I should say the element Ji of A, and Ji is the cofactor of element Ji. And please forgive me for reversing J and I when we define each element. It's just it's for convenience that we'll do this, that I do this, which you'll see shortly. And just to remind you, the cofactor is equal to -1 raised to the J plus I power times the determinant of the submatrix when the ith row and jth column, the jth row and ith column is removed. So this is again the determinant of A. Now let's replace column I. So this is column I with another column. And let's say we replace it with column K. So we could then rewrite this sum. Again, we're summing over J from 1 to K, J from 1 to N. And we're, instead of the ith row, the jth row ith column, we're going to use the kth column instead. But we'll still keep the cofactor of element Ji. And so this is equal to the determinant of A if I is equal to K. In other words, if I is equal to k, then we're not changing anything. We're not changing the column. We're just replacing it with itself. But what happens if I is not equal to k? If I is not equal to k, then we are replacing column I with one of the others. And this is important because it's like taking the determinant of a matrix with two identical columns. So let's consider an example. And I'm going to move to my next page so I have enough room. And so I have everything copied over here onto this page. So if we have A is given, it's a 2 by 2 matrix for simplicity, given by 1, 3 on the first row and 2 and 4 on the second row. And let's take our determinant by setting I is equal to 2. So I is equal to 2 there. And if k is equal to 2 here, then the above is simply the determinant of the matrix 1, 3, 2, and 4. So in other words, we'll sum element 1, 2 times the cofactor of that element with the product of element 2, 2 times its own cofactor. But if k is equal to 1, and that means that k is not equal to I. The first case, k was equal to I. So let's compute this. So again, we have j going from 1 to 2. So the first term is when j is equal to 1, and again, k is equal to 1. So we have little a, 1, 1, times j is equal times the cofactor of the j equals 1, I equals 2 element. And then now when j is equal to 2, we have little a, 2, 1, and the cofactor of the 2, 2 element. And let's see, writing that out, we have little a, 1, 1 is just 1. And then we have minus 1 raised to the 1 plus 2 power times the determinant of the submatrix when we remove the first row second column, and so that leaves a 2, and then we add that to a 2, 1, which is 2, times minus 1 to the 2 plus 2 power, which is 4, and then we take this determinant of the submatrix for a capital A22, we remove row 1, 2, column 2, row 2, column 2, and the determinant is the determinant of the remaining submatrix, which in this case is just a 1 by 1, and that's 1. And so the answer is minus 2 plus 2 is equal to 0. And so what we've essentially done is when we replace this column by a column k that's different from I. So essentially what we've done is taken the determinant of the matrix 1, 2, 1, 2, again with two identical columns. And the determinant of a matrix with any columns linearly dependent, all they have to do is be linearly dependent, and of course two columns that are identical are linearly dependent, then that's automatically zero. So we've shown that when I is equal to k, we get the determinant of the matrix. If I is not equal to k, we get zero. And what this is basically, what this is a diagonal matrix with the determinant of A on the diagonal elements. And if we divide by the determinant, we get the identity matrix. So let me write that down. So again, we're summing, oops, wrong color. We're summing over J, and we have the J kth element times the J ith cofactor all over, and then we're dividing by the determinant of A, and that is equal to 1 when I is equal to K, and 0 when I is not equal to K. And so this gives us the elements of our identity matrix. So remember that the identity matrix is delta Ki. We wrote it as delta Ij, but we can use any variable to represent each element of any matrix. These are just variables, so we can set them to whatever we need them to be. Let me rewrite this equation in a slightly different form. So instead, I'm going to write the adjoint part first, divided by the determinant A, and then multiply by element Ajk. And you'll recognize this as if you look carefully, you should recognize it as a multiplication of matrix Aj divided by the determinant with the matrix Ajk, which is simply A. And actually, I'm noticing I reverse the order of this. This should be I K. So yeah, that should be delta Ik. So if let me make sure you can see this as a matrix multiplication. And in place of all this, I'm just going to write little alpha Ij, and this is Ajk. So I'm multiplying each element of the ith row with each element of the kth column, and I'm summing. And so this, therefore, is the product of the inverse matrix with A, which gives the identity matrix. And the inverse matrix, the ijth element of the inverse matrix is alpha ij, and that's equal to the j-ith, not ijth, cofactor matrix divided by the determinant of A. And the j-ith cofactor matrix is defined as the adjoint of A. Adjoint matrix of A. Okay, so we've now shown how for a square matrix to find the inverse matrix. Again, the inverse matrix, when multiplied by the original matrix, gives the identity matrix. And let me restate what this equation is saying in words. This is saying that the element ij of the inverse matrix is the j-ith cofactor divided by the determinant of A. So now we need to, well, let's write this out here. So A minus 1, the inverse matrix, is equal to the adjoint, the 1 1 element is the cofactor 1 1. The 1 2 element is the cofactor of element 2 1. And the element in the first row nth column is a n1. And likewise, element in the second row first column is the adjoint, sorry, the cofactor 1 2. And the element in the nth row first column is the cofactor 1n. And that's all divided by the determinant of A. So this is how you compute the inverse matrix. And let's look at an example. So if we have A is equal to 1 and 2 minus 2 and 1, then we know we have to compute the determinant of A, and that turns out to be 5. And remember that the j-ith cofactor is equal to minus 1 to the j plus I power times the submatrix, the determinant of the submatrix, with the j-ith column removed. And the inverse matrix is equal to the cofactor 1 1, cofactor 2 1, cofactor 1 2, cofactor 2 2, all over 5 in this case, which is the determinant. And A11 is equal to 1, so minus 1 raised to the second power times the determinant of the submatrix when the first row and the first column is removed. So that's 1. A21 is minus 1 raised to the third power times the subdeterminant when the second row first column is removed. So that's 2. A12 is minus 1 raised to the third power times the determinant of the submatrix when row 1 second column is removed. So that gives this term, and that's minus 2. And then we get minus 1 raised to the fourth power times the subdeterminant of the submatrix when we remove the second row, second column, so that gives 1. And that is equal to 1 minus 2, 2, 1 divided by fifth, or divided by 5, and that's 1/5 minus 2 over 5, 2 over 5, and 1 over 5. And you can verify this by multiplying that solution times the original matrix to see if you get the identity matrix. And I've done that, and this solution is correct. With that, I will close with 2 theorems. Theorem 10.6.1 states that for a square matrix A, which is n by n, if the determinant of A is not equal to 0, then there is an n by n matrix A inverse such that when we pre-multiply with A, or if we post-multiply A with the inverse, you can do either, and you'll get the identity matrix back. So, so that matrix and A inverse, or A with the minus 1 power, is the inverse matrix, and A is said to be invertible. Now, on the other hand, if the determinant of A is equal to 0, then you'll notice, if you go back and look at the, let's go back and look at the determinant again. Where are we here? Right, so the inverse matrix was proportional to 1 over the determinant. So if the determinant's equal to 0, then the inverse matrix must not be defined, and that's the case. That so if the determinant of A is equal to 0, then A is not invertible. It is said to be singular. And the inverse matrix doesn't exist. Okay, and the last theorem is theorem 10.6.2. And that again says if A is again square, it's n by n, and the determinant of A is not equal to 0, then A, x equals C, has the unique solution of x is equal to the inverse matrix times C. So we found another way to solve this system of equations. And with that, I will conclude this video on the inverse matrix as a way to solve this system.